Hello, welcome to this lesson of our study of mathematics journey. Okay, so in this lesson, what we'll do is we'll go through what we mean by metric spaces. Okay, so when we say metric spaces, what do we mean? So I'll give you a general overview of metric space, and then I'll read the mathematical definition for you. So metric space is just the distance. You're looking at the distance between 2 points in a particular set of points or set of elements. Okay, so if I have maybe a set, let's say set P, having the elements P1, P2, P3, and if I have what we call a function defined on these three set elements P1, P2, P3, such that the distance between P1 and P2, or P1, P2, the distance, I'm talking about distance, is the same as P2 minus P1, okay? Like, you see, so when you have a definition like this, and it's always satisfying some condition, then you're talking about metric, the function metric. So the function, or what we mean by what metric or the metric function is generally a distance. Okay, so metrics talks about distance. So now let's come back to our screen here and discuss the mathematical definition of metric space. A metric space XD consists of non-empty sets, so this should be important, non-empty set X and a function D such that S cross X, this X cross X means that you pick an element from the set X and you operate it on another element from the same set X, and this should give you a value in this range. What this means is that it should give you some value, positive number or a non-negative number. Let me mention it that way. Okay, a non-negative number, such that the following conditions hold. So condition 1, there should be non-negativity. Okay, so this condition, non-negativity, means that for all the elements in X, so if I capital X, if I pick small x and small y from capital X, and the distance or the metric on xy, or maybe the distance between x and y, is non-negative, meaning it's greater than or equal to 0, and it's equal to 0 if and only if x is equal to y. So when I say the distance, it's just you measuring the distance between these 2 points X and Y. Okay, so the distance between these two is never negative because you are talking about distance. What's the distance between you and your friend? You can say 2 meters. Or my friend is away from me maybe 5 miles, so there is no negative 5 miles or something. Okay, so if you have X equals Y, then the distance between X and X, so if I'm standing here, then the distance between this point and itself is 0. There's no difference. Okay, that's what the metric space means. Now we go to the second condition, symmetry. Symmetry means that the distance between x and y is the same as the distance between y and x, and it's true. If you are sitting in a class, then you look at your friend at your back, the distance between you and your friend at your back is the same as the distance between your friend and you from the front, from your back, from the aspect of your friend. That's what I want to say. Okay, I hope this clear. All right, so let's go to the third condition. The third condition is saying that there's what we call triangle inequality. So the triangle inequality talks about the distance between 3 points. So maybe if I want to move from here X to Y, okay, so I have Y here and I want to move from X to Y, and there's another point, let's say Z, belonging to the same set, and I want to pass to Z before I get to Y. What the triangle inequality is saying is that the distance you move from X straight away to Y is always less than or equal to the distance you move from X to Z together with Z to Y. Okay, so the metric or the distance d of xy is always less than or equal to d of xz plus d of zy. Okay, that means you move from x to z before moving from z to y. Okay, this whole the whole thing about metric spaces. So all these three conditions, you should always have them in mind. That one, the metric or the distance between 2 points in a set is non-negative. That's the first point, greater than or equal to 0. And second one is symmetry. The distance between 2 points is always the same, meaning the distance between x and y is the same as the distance between y and x. Now the third one is the triangle inequality, which you should always have in mind. So we are going to pick some example and try to show that they are indeed metric spaces. Okay, so show that for all x, y in this R means just the real numbers, the function d of xy, which is given by the absolute of x minus y, is a metric on R, and Rd is a metric space. So if you're able to show that yes, it's a metric on y, then it's indeed a metric space. So how to solve this? Okay, now we just go and pick our conditions. Our condition is saying, the first one is saying non-negativity, so it means this metric function here, let me clean this before. So what we have here is that d of xy is always equal to absolute of x minus y. So one thing you should also know is that once you have the absolute function defined here, you should remind yourself of some properties of the absolute function. Okay, so the first case is this: d of xy should be non-negative. That's the first one. That's the first point here. Okay, so is this true? Yes, this is true, because the absolute of each number, if I pick, let's say, absolute of a, is always greater than or equal to 0. This is what we know for absolute values. Okay, I don't know if you remember your absolute values. So it means that the absolute of anything is always greater than or equal to 0. So it means this is indeed greater than or equal to 0, which satisfies the first point, the non-negativity. Now we go to the second point. So the first point is finished. The second point is that the distance, or the metric, or maybe, yeah, let's pick it as distance. The distance between x and y should be equal to the distance between y and x. So we should be able to have this relation. Okay, we should have this relation. Now this is equal to absolute of x minus y, and this is the same as absolute of negative into x plus y minus x rather. So y minus x. So when you expand this, you get this back. When you expand whatever that is here, you get whatever you have here back. Okay, so I'm not changing anything. And this is the same as what, because for the absolute function, absolute of negative a is the same as absolute of a. So if I have absolute of negative of the whole of this, then it's the same as absolute of y minus x. And the metric function, or the function we have here, is defined by d of something comma something is equal to the first one minus the second one. So if I have absolute of this minus this, then it means this is the same as d of the first one is this y comma x. So now everything here on this line is related by equality. Okay, it means d of xy is equal to d of yx, and it means the symmetry aspect is also satisfied now. Now the next thing is to show the triangle inequality, so that it will be complete for us to see that the function defined on R is actually a metric. Okay, on R. So we have d of xy being equal to absolute of x minus y. Now I want to show that this indeed satisfies the triangle inequality, which at the end we should get something like d of xy is less than or equal to d of some xz plus d of some zy. Sorry. So this is what we should get. Now let's put this, circle this, and put it somewhere. That these are end products. Okay. Now we have d of xy being equal to absolute of x minus y, and this is the same as, if I want to show that to move from x to y, there's another element z which belongs to the R. Okay, it's the set R, because everything we are dealing here is from the set R. Okay, and it's between x and y. So the element z is between x and y, and I can introduce it in the absolute function equation. Okay, so then plus z. So minus z plus z will give you what? 0. So actually I've not done anything here. I just created the z and destroyed it again. Okay, so now this in a long way is the same as absolute of x minus z plus, so you can put this in brackets, z minus y. So now this looks like this. If I have absolute of a plus b, from the absolute function properties, this is the same as, this is less than or equal to absolute of a plus absolute of b. So you should know some properties before you can apply them here. This will imply that d of xy has been expanded to this form, and I will say is equal to absolute of x minus z plus z minus y. Okay, now this whole thing can be treated as this a here, and this whole thing can be treated as this b, and they are separated by plus. So this means this is less than or equal to absolute of x minus z as our first a plus absolute of z minus y as our second b. Okay, so this is following this property. Now we say that if you have absolute of x minus something, or maybe something minus something, it defines this metric, because the metric is defined as d of something comma something is the difference, that is the first one minus the second one. So this side, this whole thing, okay, this whole thing here is equal to d of x comma z plus d of z comma y. But remember, this d of xy is equal to this, and it's less than or equal to this side. But this side that we've gotten is also equal to this side. I don't know if you get what I'm trying to say. So this is what we've gotten. This is less than or equal to absolute of x minus z plus absolute of z minus y, which is less than, oh sorry, that part is equal to, this simple part here is equal to d of x comma z plus d of z comma y. So in effect, this will imply that d of x comma y is less than or equal to this, which is the same as this. Okay, so it means it's less than or equal to d of s comma z plus d of z comma y. So yes, this function here is also a metric on R. Okay, I don't know if you get what I'm trying to say here. So let's go to the second one. The second one is a bit cumbersome, but then I'll try to explain it to your understanding. I don't know if you get it, but try and get me. Okay, assume that we want to move from one point x. So we want to move from one point x having the coordinate x1 s2. So this is the point x having the coordinates s1 s2, so x1 x2. Okay, so that's why I just put this down so that you understand. To in the plane to another point y, so this is the point y. Okay, and we are only allowed to move horizontally and vertically. So if you want to move horizontally and vertically, we want to move from this point to this point. So the first thing we can do is first we move from here to here, then move from here to also here. So the first horizontal one, then to the second vertical point. So that's why the whole statement here, if you first move horizontally from x1 x2 to y1 x2, so you move from here to here, then vertically, and then vertically from y1 s to this point to y1 y2, then the total distance d is d of xy, that is between this point, these 2 points. The total distance between these 2 points is defined by this. So we are saying that the total distance between the point x and y is equal to y1 minus x1 plus y2 absolute of them x2. Now you're supposed to show that this is a metric on R2. You remember all the point x was a two-dimensional point, and then y2 is a two-dimensional quantity. So you are supposed to show that this is a metric on R2. So the most important thing you should know is the definition of the distance. Okay, is given by modulus of y1 minus x1, or the absolute of it, plus absolute of y2 minus x2. So this is the definition, and we are supposed to show that this is a metric on R2. It means every point we pick in R2 should be a two-dimensional something, a two-dimensional quantity. Okay, so now let's try and analyze this. So the first condition we should show is that we should show that this is non-negative. Yes, and this is obviously non-negative because the absolute definition or the absolute function is never negative. That is, this part will never be negative, plus this part too will never be negative. So it's always greater than or equal to 0, which is satisfied. We are done from the absolute function definition. Now the second part is that it should be symmetric. Okay, that one too, you can show it straight away because we use the same idea as the absolute function definition or properties. Okay, so this is equal to absolute of, like we did for the first one, negative into x1 minus y1. Okay, then plus absolute of negative into x2 minus y2. When you expand then the bracket in the absolutes, you realize that you have the same things. Okay, and this is the same as absolute of, I said absolute of negative a is the same as absolute of a, so absolute of negative something is the same as that, the absolute of the same thing, the positive of the same thing. Okay, you can pick an example as absolute of 2 and absolute of negative 2, they'll give you the same thing. So it means absolute of the negative of this is the same as absolute of x1 minus y1 without a negative, then this part to x2 minus y2 without a negative. So but if you have something, this first one minus this plus absolute of this 2 minus this 2, then it's a metric. And remember, realize that in the metric definition, the one at the latter part, that is the y, is always in front here and it's in front here, and the one at the front is always at the latter part in the absolute definition. Okay, so you should check all these and make sure it satisfies this. So this means that the one at the latter part here will come forward in terms of the metric space, and the one at the front here will come at the latter part. So now we've been able to show that d of xy is the same as d of yx. So this is simple to prove, right? So now the next part that is somehow difficult to prove is the latter part, which is the triangle inequality, to prove for two-dimensional quantity. So with that, let me use a different page and we'll solve that very quickly. I'm sorry, this is equal to y1 minus x1 plus y2 minus x2, sorry. So the same thing, we can create and destroy something. So this metric is the same as, or this whole thing is equal to absolute of let me just explain it well for you. Y1 minus x1 plus z1, okay, minus z1. Okay, so z1 minus z1 is the same as 0, and you get back this same thing. Okay, so you do same to this side, y2 minus x2 plus z2 minus z2, and you get back, if you want to simplify this, you get back your first part of the equation. Okay, now this is the same as, if I want to regroup them, okay, this is the same as z1 minus x1, okay, plus y1 minus z1, and plus z2 minus x2 plus y2 minus z2. Absolute is on them. Okay, so you have to apply them here. Now if I treat this as one entity, z1 minus x1 and plus y1 minus z1, one entity like this plus this, and then plus z2 minus x2, then plus y2 minus z2. Okay, if I treat these two as this as two different entities like that, then obviously we should introduce it, because this part, okay, you can separate them and do it differently. You can choose to solve this part and show that, but, so you can write something like, but this z1 minus x1 in one bracket plus y1 minus z1 in another brackets, absolute of them. This is less than or equal to absolute of z1 minus x1 plus absolute of y1 minus z1. I introduced this by saying that if you have absolute of a plus b, it's less than or equal to absolute of a plus absolute of b. So you treat the ones in the bracket as a and b. Okay, now also you have this absolute of z2 minus x2 plus y2 minus z2, the absolutes. Okay, it's also less than or equal to absolute of z2 minus x2 plus absolute of y2 minus z2. So if you have these, then we can actually expand them. You can actually solve this straight away by saying that if this is less than or equal to this, okay, but this part, okay, we can compare this, that part, the latter part, this one, to this equation, and see that the one here minus this one here, this one minus this one, but if you combine them together with this, if you put what we've done here, these two into this, then we'll get our final solution. Okay, we'll try and get our final solution here. I want to clean something. Okay, so yes, so it means we'll have d of xy. It has been expanded up to this point. Okay, so this then is equal to this. Okay, this is equal to the whole of this, but the whole of this one I'm talking about is also less than the sum of these two, because this part is less than this and this part is also less than this. The first part here is less than this, the second part here is less than this, meaning if I sum them, this whole sum is less than the sum of these two. I don't know if you get it. The whole of this sum is less than the sum of these two. Okay, so this is less than or equal to, now it has been expanded to this, but it's less than or equal to absolute of z1 minus x1 plus y1 minus z1 plus z2 minus x2 plus absolute of y2 minus z2. Now the right part of the inequality will be equal to, I'm simplifying this part, but I'm not saying that this is equal to this. No, it's actually less than or equal to the whole of this, but I'm simplifying that part, the latter part, the right part of the inequality, to give us a simple term to be the same as this z1 minus x1 absolute plus z2 minus x2 absolute plus y1 minus z1 absolute plus y2 minus z2 absolute. Okay, and you can compare this and see that this whole part will give you a metric, because if you compare it to this one, you realize you have something 1 here, something 1 here, minus something 1, minus something 1, z2, y2, x2 x2, just that this time it's in terms of z and x, but this was x and y. So in effect, we say that d of xy is less than or equal to, now this part is given as d of x and z, because we said the latter part will always come in front. So the latter part like this will come here. Okay, so you have d of xz, and obviously the other part will be d of zy. Okay, if you go ahead and do that, you realize this part will also give you that metric. So indeed, we've been able to show that this is also true, or this holds for the question 2, okay, this scenario, and that is true. So now we can go ahead and try our hands on this. Okay, so we go and show that this is metric on R, that is R1. So I want you to go ahead and maybe try your hands on that, but I can give you a few hints. Okay, so you realize that whenever x and it's defined that d of xy is equal to 0 whenever x and y are the same, or x equals 0, and it's 1 when x is not equal to y. So to show, this is a straightforward answer that you can show, because with the first one, it means it will never be negative, because all the possible values you can get is 0 and 1, and these are not negative. Now with the second condition too, you should be able to show that indeed if you have d of xy is the same as d of yx, and this whole definition is the same as 0 and 1, y equals x or x equals y, the same definition, the same thing, doesn't change anything. Okay, and so the latter part is where you find a problem. The latter part, you can use a table where whatever you do is true, but then if you want to see the outcome, you can use a table where you look at the d of xy against d of maybe xz and d of zy, and then the summation d of xz plus d of zy, the summation of these. Okay, so you can look at them like that. So this will always give you a 0 and 1, but this also can be 0 and 1. Okay, and this also can be the 0 if so you are looking at d of xy being less than or equal to d of xz plus d of zy. So you want to show that indeed whenever you have this, it's less than or equal to the summation of these two. So whenever this is 0, it can be 0 or 1. It can match against d of xz, which can be also 0 and 1. So 0 can match 0 and 1, and this one too can be, this 0 can also match 0 and 1 here, and this can match 0 and 1 here. So this is how you go about it: 0 and 1, then 0 1 0 1. So when all of them are 0, the sum will be 0, and indeed 0 will be less than or equal to 0. I don't know if you get it. So the equality holds. When this matches 0 and this is 1, okay, this is 0 and this is 1, the summation will give you 1. I don't know if you get what I'm trying to do here. And indeed 0 is less than or equal to 1 because 0 is less than 1. But when this is also 0 and this is 1 and this is 0, you still have 1. Okay, and if this is 0 and this is 1 and this is maybe 1, you have 2. So you can be checking up those things, and indeed whichever way you go or whatever you do, you still have the condition hold. Okay, so that is it, and it proves that indeed we have a metric space. So thank you, and don't forget to subscribe to my channel if you have not subscribed. See you next time.